Pluto, a far-off and baffling smaller planet, was once an individual member of our solar system's planetary family. However, later alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back with a stunning entrance into the spotlight. They claimed that the frosty world is on a potential crash course with Neptune. But how could this occur, and what might be the outcomes of such a significant event? Are we witnessing an interesting cosmic phenomenon, or is there something else to this looming infinite crash? Join us as we investigate the outcomes that could come from a Pluto-Neptune collision. Pluto, a planet that was downgraded to a dwarf planet in part because of its baffling orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is dangerously close to that of Neptune. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous crash between these two planets, one that could pose an immense threat to Earth. But how is such an event even conceivable? Pluto's trip around the Sun is like no other planet in our solar system. It takes 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, diverging entirely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, determined to be 17 degrees from the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating features of Pluto's orbit is its synchronization with Neptune's. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why have Pluto and Neptune not collided? The answer can be found in gravitational influences from other planets. The study of Pluto's orbit began shortly after its discovery, as astronomers struggled to comprehend its distinct path. Unlike other planets, whose orbits lie somewhat near the ecliptic plane, the steepness of Pluto's orbit made it stand out. The realization that Pluto's orbit actually intersects Neptune's made the mystery even more complex. Yet, within these complexities lies evidence of the stability of Pluto's orbit. The intricacies of celestial mechanics, particularly the three-body problem in space, help explain how Pluto, Neptune, and the Sun interact through gravitational forces. This problem describes how three celestial objects influence each other with their gravity, making their motions difficult to predict. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. Terms like asymptotic libration, scope libration, and the VIC oscillation are key to understanding this puzzle. According to astrophysicists, libration is what helps keep planets in their orbits. Regarding Pluto and Neptune, libration ensures that whenever Pluto crosses Neptune's orbit, their positions are always at least 90 degrees apart. This spatial separation is crucial in preventing a collision. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an extra layer of protection from potential impacts. Another critical factor is the VIC oscillation, named after three researchers, Ka, Vov, and Appleby, who studied how celestial bodies interact. This oscillation explains how Pluto's movement around the Sun remains stable despite appearing chaotic. Despite the apparent disorder, these oscillations help maintain Pluto's orbit, preventing it from colliding with Neptune or straying off course. This understanding of the three-body problem allows scientists to predict how orbits change due to gravitational interactions. Simulations in the late 1980s revealed that, despite its seemingly chaotic nature, Pluto's orbit maintains stability over extremely long time scales. Recent computational studies have shown how giant planets like Neptune, Jupiter, and Saturn influence Pluto's motion. Neptune's orbit around the Sun has a unique resonance with Pluto. Every time Pluto completes 2 orbits, Neptune completes 3. This resonance helps stabilize Pluto's trajectory. But Neptune isn't the only planet at play. Jupiter's gravity also significantly influences Pluto's stability, while Saturn provides additional reinforcement. These studies demonstrate that Jupiter's gravity alone is strong enough to keep Pluto on a consistent course for billions of years. It's as if Neptune, Jupiter, and Saturn work together to ensure Pluto continues moving safely through space without major disruptions. These peculiarities are vital in maintaining the order and stability of celestial movements. Without such gravitational interactions, the solar system would be far more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their orbits. For Pluto, particularly with discussions of a possible collision with Neptune, understanding its orbital future is crucial. This knowledge provides deeper insight into the solar system's dynamic nature. Pluto's case illustrates how even seemingly unstable orbits can achieve long-term balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena, as they help us better understand our place in the universe. Exploring the depths of space often forces us to confront the eccentric nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, the idea that small variations in an object's speed or position can drastically alter its long-term trajectory, is clearly demonstrated in Pluto's case. Even slight shifts in Pluto's motion could lead to significant changes in its orbit over time. Using advanced simulations, astronomers can model how Pluto interacts with other celestial bodies, providing invaluable insights into the workings of our solar system. These simulations allow researchers to adjust variables and predict potential orbital shifts, offering a better understanding of Pluto's long-term stability and the fascinating dynamics of planetary motion. The broader implications of Pluto's stability. The stability of Pluto's orbit isn't just an interesting quirk of celestial mechanics, it has broader implications for how we understand the long-term evolution of planetary systems. Scientists study Pluto's motion to gain insight into how gravitational interactions shape the architecture of the solar system and beyond. One of the most intriguing aspects of this research is the role of mean motion resonance, a concept that extends beyond Pluto and Neptune. In fact, similar resonant interactions are observed in exoplanetary systems, where planets orbit distant stars in synchronized patterns. Understanding how resonance protects Pluto from colliding with Neptune can help astronomers predict the stability of exoplanetary orbits in alien solar systems. Moreover, the same gravitational principles that govern Pluto's motion also apply to asteroid belts and other small celestial bodies. The Kirkwood gaps in the asteroid belt, for example, are regions where resonances with Jupiter prevent asteroids from maintaining stable orbits, either ejecting them from the belt or sending them into potentially hazardous paths toward planets. This highlights how resonances can act as both stabilizers and disruptors, depending on the system's specific configuration. Could an external force disturb Pluto's orbit? While Pluto's resonance with Neptune appears stable for the foreseeable future, the possibility of external disruptions remains an open question. Could an unknown force or celestial body alter Pluto's trajectory? One hypothesis that has captured the interest of astronomers is the existence of Planet 9, a hypothetical massive planet lurking in the distant regions of the solar system. Some researchers believe this unseen planet could be influencing the orbits of trans-Neptunian objects, TNOs, possibly exerting a slow but steady gravitational pull on Pluto. If Planet 9 exists and is as massive as some estimates suggest, perhaps 5 to 10 times the mass of Earth, its gravitational influence could cause long-term shifts in Pluto's trajectory. However, current models suggest that any effects would occur over millions of years, rather than posing an immediate risk of destabilizing Pluto's orbit. Another potential disruptor is the passage of a rogue star through the outer edges of our solar system. Astronomers have documented evidence of past stellar flybys that may have nudged objects in the Oort cloud, sending comets inward toward the Sun. If a future stellar encounter were to occur, it could subtly alter Pluto's path, but again, such an event would unfold on timescales spanning millions of years. Pluto's future, what lies ahead? Despite the many variables at play, current simulations suggest that Pluto's orbit will remain stable for at least millions to billions of years. The synchronized dance between Pluto, Neptune, and other gas giants serves as a remarkable example of how complex yet orderly the solar system can be. Looking ahead, ongoing advancements in computational modeling will allow scientists to refine their predictions about Pluto's fate. As new telescopes and space missions provide more precise data, we may discover even more intricate details about the forces shaping Pluto's orbit. Furthermore, as humanity explores deeper into the outer solar system, perhaps through future missions to the Kuiper Belt, our understanding of Pluto's place in the cosmic puzzle will only continue to grow. In the end, Pluto remains a testament to the delicate yet resilient balance of celestial mechanics. What once seemed like an unpredictable and chaotic orbit is now recognized as a beautifully orchestrated movement governed by the invisible hand of gravity. You can see how even tiny changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something really interesting about Pluto's orbit. Despite having mechanisms like asymptotic and scope libration to maintain its stability, its orbit could still be wild and unpredictable. Beginning with even a minute difference in Pluto's location or how fast it's moving, over many years, its course might end up looking very different. However, despite this chaos, for a long time, Pluto's orbit remains stable, on the scale of billions of years. This means that during Pluto's orbit around the Sun, there is a kind of order to it, even though it seems all over the place at first. Predicting large events, especially when they include Pluto's erratic orbits, presents huge challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with ambiguity. While using mathematical simulations is a strong tool to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. These models depend heavily on the accuracy of initial conditions and the extent of the interactions they simulate. Any slight mistake or distortion can lead to drastically different outcomes, making accurate predictions a difficult task. Furthermore, the chaotic nature of planets like Pluto serves as a reminder of the ever-evolving and dynamic nature of the universe. While we have made huge strides in understanding space, the case of Pluto reminds us of how our knowledge of the universe still remains limited. Comprehending the forces influencing the giant planets on the orbit of Pluto provides useful information about the solar system's broader dynamics. It shows how the presence and position of each planet can have sweeping effects, influencing the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns regarding a possible collision between Pluto and Neptune? Despite all of these complex forces working to prevent such a situation, some experts continue to explore the possibility. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique insight into the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unexplored reaches of space. His position on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He doesn't think the new classification is a bad thing but rather a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He views the intricacies of Pluto's orbit, as well as its interactions with Neptune, through a lens that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it may undergo significant changes in the distant future. Tyson's insights are further bolstered by Michio Kaku, another astrophysicist who brings a different but equally valuable viewpoint on the solar system's evolution. Kaku highlights the risks associated with our understanding of celestial mechanics, such as the possibility of a collision between Pluto and Neptune. Both scientists emphasize the importance of constant observation and vigilance in space exploration. Despite the apparent safe and stable nature of Pluto's orbit, they warn that a collision with Neptune remains a possibility. These warnings are a reminder that, even as we chart and measure the vastness of the universe, uncertainties remain that could drastically alter our understanding and predictions. Would Pluto collide with Neptune? It seems improbable, but the vastness of space always presents unexpected opportunities. While Pluto's orbit remains stable for now, the long-term dynamics of celestial mechanics remain unpredictable. The future of the solar system holds surprises that have the power to shake even the best-made models. The potential for a collision between Pluto and Neptune, while seemingly remote, is a compelling reminder of the complex and unpredictable nature of space. As mentioned, Pluto's orbit is governed by intricate gravitational interactions with Neptune, Jupiter, and other massive planets. These forces work together to maintain a delicate balance that prevents Pluto from veering off course or crashing into Neptune. However, in the vast timescales of the universe, the dynamics of celestial bodies can change. What appears to be a stable orbit today may not be so in millions or even billions of years. One key factor contributing to the still improbable but possible collision is the phenomenon referred to as orbital precession. Over time, the orbits of celestial bodies can slowly shift and rotate, altering their paths in space. This is especially true for bodies like Pluto, whose orbit is more skewed and eccentric compared to the more circular and aligned orbits of the larger planets. As Pluto's orbit could force it closer to Neptune in the distant future, a disastrous event could become possible. The degree of this shift is still uncertain, but it's something that researchers continue to monitor. Interestingly, Pluto and Neptune have a unique resonance that further complicates the possibility of a collision. This resonance, a 2:3 orbital resonance, means that for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance acts as a safeguard mechanism, ensuring that Pluto and Neptune never come close enough to collide, despite their orbits crossing each other's paths. The gravitational forces between them are in sync, preventing a crash. The resonance essentially synchronizes their orbits, keeping them in a stable relationship. Nevertheless, this delicate resonance highlights the sensitive nature of their orbits. Even small disruptions, such as changes in the gravitational forces exerted by other planets or nearby celestial objects, could potentially throw off this balance, increasing the probability of future collisions. The fragile stability of Pluto's orbit. While the current orbital resonance between Pluto and Neptune prevents a direct collision, the long-term stability of this relationship remains uncertain. Small perturbations in the solar system, such as gravitational influences from passing asteroids, rogue planets, or even distant stars, could introduce shifts in Pluto's orbit over millions or billions of years. These tiny variations might accumulate, gradually altering the balance that has kept Pluto and Neptune apart for so long. Moreover, the presence of additional celestial bodies in the Kuiper belt, where Pluto resides, further complicates its orbital dynamics. Objects in this distant region experience gravitational interactions that can subtly nudge them over time. If another massive Kuiper belt object, KBO, were to be perturbed into a more eccentric orbit, it could set off a chain reaction, affecting the gravitational balance of Pluto and potentially altering its resonance with Neptune. The role of planetary migrations. Beyond local influences, there is also the broader issue of planetary migration. Theories suggest that during the early formation of the solar system, the giant planets, Jupiter, Saturn, Uranus, and Neptune, migrated from their original positions. This movement reshaped the orbits of many smaller bodies, including Pluto. If planetary migration were to continue at even a minimal scale, due to interactions with smaller celestial bodies or leftover debris, the long-term positioning of Neptune could shift ever so slightly. This might eventually impact Pluto's orbit, increasing the risk of unpredictable changes. Could a future event disrupt the balance? While current models suggest that Pluto's orbit is stable for millions of years, rare cosmic events could challenge this assumption. For instance, if a large interstellar object, such as an errant planet or a rogue star, were to pass close to our solar system, its gravitational influence could disrupt the delicate balance of the outer planets. Even a slight modification in Neptune's orbit could cascade into broader effects, indirectly affecting Pluto. Another possible event involves the Sun itself. As the Sun ages, it will gradually expand into a red giant, altering the gravitational equilibrium of the solar system. This change in mass distribution could subtly modify the orbits of outer solar system bodies like Pluto, pushing them into slightly different paths. While this transformation will occur over billions of years, it adds another layer of unpredictability to Pluto's long-term future. Pluto's fate in the distant future. Given its current orbit and resonance with Neptune, Pluto is not in immediate danger of colliding with another planet. However, the chaotic nature of celestial mechanics means that no orbit remains truly unchanged over infinite timescales. Scientists will continue monitoring Pluto's motion, refining simulations to predict potential deviations in its trajectory. In the grand scheme of the universe, Pluto serves as a fascinating case study of how intricate gravitational relationships shape the movement of celestial bodies. Its orbit, while seemingly stable today, carries the potential for unexpected evolution over vast cosmic timescales. The bigger picture, what Pluto teaches us. Pluto's orbital behavior highlights the broader challenges in understanding planetary dynamics. The study of celestial mechanics is not just about predicting planetary motion, it also provides insights into the forces that shape the universe. By studying Pluto and similar bodies, astronomers refine their understanding of how planets form, migrate, and interact over time. Furthermore, Pluto's case reminds us that the solar system is not a static structure but an evolving system influenced by countless factors, both internal and external. As technology advances, future space missions and telescopic observations may provide deeper insights into Pluto's long-term orbit, helping us refine our predictions for its fate in the distant future.